Okay, so a couple of things by way of background. As you heard earlier today, increasing yields is one of the background items. In this country, we've seen an increase of about a factor of 2 or perhaps 3 in wheat yields over about the last 30 or 40 years. But the interesting point is that a lot of the work that was done on trace elements or micronutrients was some time ago. It was back at the beginning of that curve, actually, back in the sort of 60s, and not much has been done since. The other thing which you may already know is the law of the minimum, this idea of the leaky barrel. So I've put on some example nutrients there. They may or may not be correct for a particular situation, but the idea is that the thing which is in shortest supply actually can have some effect on yield, and actually moving those stays up or lengthening the stays can protect against the loss of yield. So the question then is, are trace elements becoming limiting in any way? And particularly on high-yielding crops, on particularly risky soils. So there are a series of questions really compared to what's happened over the last, say, 30 or 40 years against that background I showed you. First of all, are soils changing? And we're looking here at copper, manganese and zinc. Do high-yielding wheat varieties respond more? And then there are reports in the literature, and you see this in the farming press. There was one just in Farmers Weekly in October of yield increases, some of them quite startling, 3 tons per hectare increase due to micronutrient sprays. And these come out periodically, as I'm sure you've seen in the trade press. And there is another slight background article here, which is the business of decreases in the concentrations of these nutrients. In other words, it's a quality issue in terms of grain, and we published this in 1998, and also more recently a genetic analysis behind the reasons for decreases in micronutrient density or quality of grain. And then there are further questions. Does soil analysis help to predict when yield will be affected, if it is? And also, will leaf or tissue analysis help to decide? So let's kick off with the soil's micronutrient status. What I'm going to show you in a moment is, in this project, we sampled from around the country 132 sites in 2009 and 10 at the beginning of the project. I'm going to refer to these as the new soils. And then we put it against some data from years ago. We did a soil inventory, and the samples were taken in the early 80s. There are a lot of samples in this. It was a completely national survey of around about 6,000 types of soils with all sorts of land uses. What I've done here is to cut down that data set by using EU land use data to just the agricultural soils in the data set. And that comes to still a lot, 1,800 agricultural soils, and I'll refer to these as the old soils data. What we've determined here is the very common EDTA extractable, manganese, copper and zinc, and here are the results for manganese. So for manganese, I'll take you to this one. The new is on the left, old is on the right, and of course, as we were saying, there are a lot fewer samples in the more recent sample set. But what you see here is in the middle of each box is the median concentration. The boxes are actually the quartile range, and outside of the boxes, if you like, are the outliers and the wide spread of data. So the first point is that if you have more samples, you get a much wider range of data. And in that case, on the old data, we have a lot of high samples, which tends to drag the median and the distribution upwards. But if you look at the new and the old, and particularly focus on that line in the middle, the median, you could say there's been a slight decrease over something like 30 or so years. And now the data for copper on the left and zinc on the right. And again, if we just focus on the median, you can see, if anything, it's slightly lower in the recent data, the new data, than in the old data. But I'll emphasize, A, it's slight, and B, the older data contains a lot more sites and tends to get dragged up by those higher outliers to give you slightly higher levels. The second aspect of the project that I want to go into is really to think about how you decide. What's the sort of guidance on the need for micronutrient applications? And First of all, I think in all cases would be the soil type. We've talked about precision farming. You need to know which soils are likely to be deficient. And these are the light soils, of course, organic soils, those of high pH. And the risk in all those situations is due to low availability of micronutrients in the soil. Then we often use soil analysis. So as I mentioned, EDTA extracts, particularly in this country, are the most common form of soil analysis. Visible symptoms is another issue, which we'll talk about in just a moment. Leaf analysis, of course, can be useful, taken usually in the spring before any problems. And so if we look, first of all, at the soil analysis, the EDTA extracts, these are the criteria in milligrams per kilogram of soil that people tend to use. For manganese, you'll see the column there says none. That's because manganese solubility and extractability just varies so much in the soil due to the conditions, the moisture content, the dryness or wetness of the soil can make your extractability apparently go up and down. So soil analysis is actually not very useful for manganese. For zinc, we think it's probably less than 1, but there's not a lot of research in this country on zinc issues, zinc deficiency. Much more common in other countries, North America, Asia, Turkey, Australia, etc., but not in this country. And then copper, as you can see, it's banded by the type of soil. So the criteria for organic soils are slightly higher than chalky soils, and other soils 1.6. So let's have a look at those criteria. We'll put them all together in a minute with other signs or symptoms. Visual symptoms. We actually assess these in our trials, and you can see here, these are not pictures from the trials, by the way. These are pictures that were given to me by Yara and NIAB. And you can see the very classic symptoms for each of these deficiencies. And many of you will have seen these in the field. They can be transitory. We did assess them at growth stage 33, and in our trials, none were observed. And the other issue about visual symptoms while we're talking about them is that they can be confused with other problems. Effects of the weather on crop growth or the appearance of leaves, and for example, diseases, as we saw earlier this morning, some of them, to me anyway, can look a little bit like a disease. So not entirely diagnostic, because unless you know very precisely, it may be misinterpreted. And then tissue analysis threshold, again, based on quite old data, which people tend to think is absolutely rock solid, they would say, okay, in copper, you're looking at less than 4 ppm in the leaves, 2 ppm in grain, and for manganese and zinc, 20 ppm is used as a threshold in leaves and grain. So let's test drive all those sort of critical values with our field experiments. So I'll just explain about the experiments. We did 5 sites each year in areas likely to be trace element deficient. They're all listed up there. They tend to be light, organic, or calcareous soils. We had 6 light, 6 organic, and 3 calcareous sites in the 3-year program. And in each case, we grew solstice on all sites to ensure comparability of the crop variety. The treatments are shown here, put on at growth stage around about 30 and 32 as per recommendations for a severe deficiency. And you can see here the treatments. We had untreated controls as well as copper only, manganese only, or zinc only. And you can see the rates that we applied there and the total amount of each of those elements added. But I must stress that was what was recommended on the packet, as it were, for a severe deficiency. So we put enough on. The soil analysis, if we have a look at what happened here with the soil analysis, these are 2010 data. And again, what I've done at the bottom is just list the criteria again, and then put in red anything which is definitely, according to the criteria, deficient. And in this case, copper is particularly deficient, as you can see with the red figure. The other thing to note on here is that line near the bottom which says new soils 25 percentile. That's from our new data. We've taken the 25 percentile, in other words, what's the number associated with the last 25% of soils which are low in terms of manganese, zinc and copper. And you can see a lot of our sites are, compared to the national coverage, they're actually close to or below, in some cases, 25 percentile. So we have picked deficient sites or low sites. 2011, none of them came up as deficient by the soil criteria. And 2012, again, copper came up as deficient on the Waterbeach site, which is an organic site, in 2012. We go then to leaf analysis. This, I've only shown 2012 data here. The lines in each case, the horizontal lines, show those critical values. And you could say here, from the point of view of leaf analysis, you'd say that in that 1 year, 2 of our sites are deficient in copper, 2 were deficient in manganese, and 3 were deficient in zinc. But now let's have a look at, this is really the test here, what happened to grain yields. Well, in 2010, starting in the beginning of our experiments, you can see here the type of soil that we've got, and then the treatments, the means there, and the coefficient of variation of our experiments, the experimental variation, and finally on the last line, the significance, if any. And in 2010, no significant differences in yield from our treatments. Even though we have, we've got some high yields, 9, 8, we have some low yields in that particular year. 2011, slightly higher yields in some cases, 10 or 11 tons. So high yielding crops on risky soils, getting these elements at the right sort of rates, no significant difference in yield. And then finally 2012, bingo, there's an increase in yield due to copper addition on that organic soil at Waterbeach. But that is the only one out of 15 experiments. There's a copper response in terms of yield in 2012 on one organic site. So you might ask, what is the sort of sensitivity of our experiments? What size of increase in grain yield would we actually detect? And to do this, if we look at the coefficient of variation from the analysis of each experiment and express that variation in terms of yield, tons per hectare in other words, then any yield increase that we're looking for due to the treatment effect would have to be greater than that to be detected really in the experiment. And the table shows the range, because it depends on the site and the particular experiment, across the 3 years, and the mean coefficient of variation in terms of yield. So basically what it boils down to is you'd have to get about a 0.5 ton increase in yield in order to see a difference due to our treatment. So that's the sensitivity of the trials, if you like. There could be effects at a lower level. When we look at combining our data, instead of looking at separate years, but put all the years in together in a REML analysis, this analysis shows us that of course, the calcareous sites in our program gave us the highest yields, the organic sites slightly less, and the light sites were the ones which had the lowest yield potential. But what we're looking for in this probability on the last line is for interactions between the soils and our treatments. And those interactions, in the case of yield, overall over the 3 years, were not significant. And you can see if you look across the control copper, manganese and zinc for each type of soil, there is only a very small difference in yield. If we then apply the same type of analysis to what the crop saw, in other words, did it take up some of that sprayed copper or manganese or zinc and put it in the grain? Well, the answer for copper is there's no significant difference in the grain, although it does again vary with our calcareous soil being perhaps slightly higher in copper, organic was the middle, and the light soils particularly being the lowest. Manganese, a similar story to copper, there's no significant difference here due to the treatments. And again, it goes in that order with the calcareous soil, actually giving more manganese in grain than the organic and the light soils. And then finally, zinc. There is a significant difference due to the treatments. where on the calcareous and the light soils we were able to show an increase in zinc in the grain. So those who were interested in biofortification of grain for micronutrients, for nutrition of animals and humans, etc., the one that really gets to the grain is zinc particularly, but not on all soils. It seems to be held back a little bit from in the organic soils, but you'll notice they're already quite high. 36 parts per million in grain is more than adequate. When you get down towards 20 or so in grain of zinc, you're beginning to say it's rather low for nutritional purposes. Okay, so to summarize my sort of road test of the diagnostics, the criteria, if you like, I've got a series of slides just with columns coming up now. So if we look at soil analysis, what this is saying, if you put organic soils, light soils and calcareous soils on the chart, it's saying that the soil analysis was only telling us something was a problem or potential problem with copper in a couple of cases. All the rest said, no, not a problem. Leaf analysis is actually coming up with more hits, if you like. And I've listed there the sites, the years, and what it was coming up in terms of telling us there may be a problem. Copper, manganese, even zinc, it was saying there's a problem at quite a few sites in a number of years. Then when it comes to the grain concentration and whether it was boosted by the application of these micronutrients, as I mentioned in just the last slide, there's really no effect on grain concentration apart from zinc. It's great news for those who want to biofortify grain with zinc, but you can't get the other ones into the grain. And then finally, the yield response. The one that stands out is the only site, 2012, where we get 1.4 tonnes per hectare increase due to the copper applications. So in summary, that chart summarizes an awful lot of data, obviously, but what it tells us is that although the organic soils are there at the top in the first three columns, we actually had 2 organic sites which didn't come up under any of the criteria as being an issue. It's Ely and Streatham sites. And you'll notice also on the soils diagnostic that only copper came up as being an issue. This may be correct because it was our yield responses to copper. For leaf analysis, this was interesting. There were no hits for a 2010 year at all. And that tells us that despite what the crop may be seeing and the critical values themselves, they can vary in terms of what's in the leaves from year to year, depending on the climate. And then finally, as I mentioned, only grain zinc can be boosted by these sort of sprays. So now I'm coming to the sort of boiling it all down into some conclusions. The data I showed you about the trace element status of soils shows, if anything, a slight decrease over the last 30 years. I'd say it's probably linked into the size of the survey that it's possible to do. We can't do 6,000 soils in this sort of project. If there is a decrease, it's a small one. I think we do need to use all the information available on the type of soil, visual symptoms, if any, soil and leaf analysis. But we know that already from the farmers that we had the field experiments in their farms. They would routinely have blasted all of our sites with the trace element fertilizers. We had to actually keep them off in order to do our experiments in a controlled way. So they would have all been using trace elements. But at the end of the day, there was only one yield response over 15 site years, which was to copper. And even that response may potentially have been fungicidal because the treatment was copper oxychloride, which can have a fungicidal effect. It could be that, particularly in 2012, as we've heard, rather than a nutrient effect. And I think what I've shown in terms of the summary table was that soil, leaf and grain concentrations of these micronutrients can be categorized as low, and people tend to believe those criteria because they've been published somewhere, without any measurable effects on yield in a lot of cases. But I think what we do know is that we now have 3 years of data from 15 sites. And of course, it's valuable data from impartial and replicated trials, and that will go into the report which is due next year. I would also like to thank my colleagues in NIAB and Hillcourt Farm who contributed to the programme, and also to say that there is an HGCA review which is going on at the moment and a meta-analysis of micronutrient data where our data would be fed in, and that will also be very important, I think, when everything comes together in the future. And I thank you for your attention.